You're here? You've traveled in the wrong time. I'm from the future together with other scientists. Have you ever wondered what is this and this? Let's talk about acids and bases and Bronsted concept. Now,
But before that, let's have our objectives for this exploration. In a quote by Open Permar, it states that process of fall in love is like acid-base titration. Drop by drop, you evolve and titrate yourself. And finally, you lost your heart and become like them. Because love needs sacrifice to suit yourself with a person wholeheartedly.
Hence, to achieve this, let's voyage.
in explaining the Bronsted concepts of acids and bases, Christopher will be in charge. You've got this, Christopher.
Alright, what's Bronsted concept of acids and bases and who coined this? Well, in 1923, chemists Johannes Nicolaus Bronsted and Thomas Martin Lowry independently developed definitions of acids and bases based on compounds' abilities to either donate or accept protons, which are hydrogen ions. In this theory, acids are defined as proton donors, whereas bases are defined as proton acceptors. But, take note that they differ from one proton or differ from hydrogen ions.
Hep, not just that we have the Bronsted-Lowry acid and Bronsted-Lowry base. When we say a Bronsted-Lowry acid, it is a proton-hydrogen ion donor. On the other hand, we had a Bronsted-Lowry base. When we say Bronsted-Lowry base, it is a proton-hydrogen ion acceptor. Hence, these two will be paired with conjugate base or acid. Do you have any questions? I guess none. Therefore, I command you to give one example of this.
Me! One of the examples of Bronsted concepts of acids and bases is this one. We have the hydrogen chloride plus water yield to produce chloride ion and hydronium ion. Hence, you may be wondering where's the base or acid here? Well, our acid in our reactant is a hydrochloride while the base is the water.
Exactly, Bea. Moreover, this arrow signifies strong acid or base, which will yield to produce the conjugate base, chloride ion, that dissociates 100%, and conjugate acid being hydronium ion. Therefore, HCl has a particular pair chloride ion as its conjugate base paired to its acid, and H2O has a particular pair, the hydronium ion. However, there's another catch, which will be explained by Jarrell.
Thank you, Axel. At this juncture, Bronsted-Lowry theory of acid and bases took the Arrhenius definition one step further. Therefore, a substance is no longer needed to be composed of hydrogen or hydroxide ions in order to be classified as an acid or base. For example, let us consider the following chemical equation. HCl plus ammonia, which both are aqueous, will to produce ammonium ion plus chloride ion. Hence, notice here that only one proton differs here as there's a missing one hydrogen here, and one proton differs here too as this has one hydrogen atom while this has no hydrogen atom.
Astounding, Jarl! Our acid here is the HCl and our base is the NH3. Here, hydrochloric acid donates a proton to ammonia which accepts it, forming a positively charged ammonium ion and negatively charged chloride ion. Therefore, HCl is a Bronsted-Lowry acid or donates a proton, while the ammonia is a Bronsted-Lowry base or accepts a proton. Also, chloride ion is called the conjugate base of the acid HCl, and H4 positive is called the conjugate acid of the base NH3.
Yes, you've expounded it well, Nina. Yet, I'll add my takeaway for this example, wherein HCl has a particular pair called chloride ion as its conjugate base paired to its acid, and ammonia has a particular pair known as ammonium ion. Well, it is just the same thing. However, let us voyage to another example. In this theory, an acid is a substance that can release a proton like in the Arrhenius theory, and a base is a substance that can accept a proton. A basic salt such as sodium plus fluoride ion generates hydroxide ions in the water by taking protons from the water itself to make hydrogen fluoride.
Impressive, Thea! Going back here, we have the examples. chloride ion plus water has a weak acid or base that produces hydrogen fluoride and hydroxide ions. When a Bronsted acid dissociates, it increases the concentration of hydrogen ions in that solution. Conversely, Bronsted bases dissociates by taking a proton from the solvent to generate.
Not just that, we have several real-life examples here, such as the acid dissociation, acid ionization, base dissociation, and base ionization constant.
Move on to that. To determine whether a substance is an acid or base, count the hydrogens of each substance before and after the reaction. If the number of hydrogens has decreased, that substance is the acid that donates hydrogen ions. If the number of hydrogens of each substance has increased, that substance is the base that accepts hydrogen ions. These definitions are normally applied to the reactants on the left. If the reaction is viewed in reverse, a new acid and a base can be identified. The substances on the right side of the equation are called as the conjugate acid and conjugate base compared to those on the left. Also, note that the original acid turns in the conjugate base after the reaction is over. Always take note that acids are proton donors and bases are proton acceptors.
For a reaction to be in equilibrium, a transfer of electrons needs to occur. The acid will give an electron away and the base will receive the electrons. Acids and bases that work together in this fashion are called conjugate. Pair made of conjugate acids and conjugate bases, such as this one. But before that, this double arrow means that it is reaching chemically equilibrium, where here hydrogen and an acidic compound plus basic compound are in equilibrium with A ion and hydrogen Z ion. As A stands for an acidic compound and Z stands for basic compound.
Moreover, A donates H to form HZ ion. Z accepts H from A, which forms HZ ion. And A ion becomes conjugate base of HA, and in the reverse reaction, it accepts a H from HZ to recreate HA in order to remain in equilibrium. And lastly, HZ ion becomes a conjugate acid of Z, and in the reverse reaction, it donates a H2A ion, recreating Z in order to remain in equilibrium. For instance, ammonia ion water are in equilibrium with ammonium ion positive hydroxide ion, where ammonia is the weak base has a particular pair ammonium ion as its conjugate acid, and H2O as the acid is a particular pair hydroxide ion as the conjugate base that partially dissociates. Hence, it is observable that only one proton differs here and one proton differs here too, as this has two hydrogen atoms while this only had one hydrogen atom.
Very well said, Linya. However, this acid or bases doesn't only act as one row. Can you guess what it is? Well, these are the amphoteric or amphiprotic, wherein this is the substance that can act as an acid or base. Astounding, right? Now, focus your eyes here. We can see that the bicarbonate ion as the base plus water as the acid are in equilibrium with H2CO3 plus hydroxide ion. Hence, we can say that HCO3 ion has a particular pair carbonic acid as the conjugate acid, while water has a particular pair hydroxide ion as the conjugate base. But, we're not yet done. As what if we make HCO3 ion as the acid, while water as the base? Well, this would be equilibrium with the carbonate ion plus hydronium ion, wherein bicarbonate ion as the acid has a particular pair carbonate ion as the conjugate base, while water as the base has a particular pair hydronium ion as the conjugate acid, wherein it is evident that they differ from one proton or they differ from one hydrogen ions.
Therefore, our major takeaway is that a Bronsted lauric acid is a proton donor. On the other hand, we have Bronsted-Lowry base. When we say Bronsted-Lowry base, it is a proton acceptor. Hence, these two will be paired with a conjugate base or acid. Strong acids and bases ionize completely in an aqueous solution, whereas weak acids and bases are partially ionized in aqueous solution. Water molecule is amphoteric in nature, which means it can act as Bronsted-Lowry acid as well as Bronsted-Lowry base. Lastly, they differ from one proton or differ from hydrogen ion.
That's how significant Bronsted concepts of acids and bases are. Thus, join us travel back in your present time. Hope you'll grasp those lessons inside your mind. Fasten your seatbelt as we are going to travel through time. In 3, 2, 1.